multivariate methods and repeated measures, predominantly by considering a number of applications, a number of case studies that will come back as we go through this course. And now, in Chapter 3, what we're trying to do is give a little bit of mathematical foundation. And of course, in a course like this, it's not a mathematics course. It's not the idea to really train ourselves in every fine point of mathematical detail that's underlying repeated measures and longitudinal data and multivariate data, but there are a few conventions that we need to agree upon. Perhaps the easiest way to think about it is many things that you know from univariate data apply, but in vectorized form. And when I say vectorized form, I mean literally a vector, like a single mean becomes a mean vector. And almost by default, a vector is a row vector. As you see, a vector is a column vector. A row vector also happens, but then it's usually made clear. Why is that? Well, if you measure, for example, in the iris data set, sepal length, sepal width, petal length, petal width, there are 4 variables. There are 4 components, and therefore there are 4 mean components also, and that's what we need to consider. The same applies also to variances. If you have 1 variance univariately, you have, of course, 4 variances multivariately. If you have, though, the univariate case, there is something that simply does not happen, and that's covariance. So the real addition to it all, and that's in a way also why this course exists and is different from univariate courses, is association, dependence, and often quantified as correlation. So covariance, correlation is what's added, but that's actually not something we can easily put in a vector. We can, but that's very inconvenient. We put that in a matrix. So we have a mean vector and a variance covariance matrix. So where we are on this slide is the eternal mean, the sample average, nothing much of a discussion there, I don't think. The sample variance, one way of capturing the spread, we all know that. We can divide by n. We can divide by n minus 1. And as has been discussed and as we know, they're both correct, but they come from different backgrounds. Dividing by n is following the likelihood principle. Maximum likelihood, normal likelihood will lead to dividing by n. If you, on the other hand, say, no, I want to start from the principle of minimum variance unbiased estimation, then you get to n minus 1. It doesn't matter in the long run, it doesn't matter for large samples, in other words. So, what is the sample covariance? Covariance is literally what it is. How do 2 things, 2 variables, vary at the same time? Another way to think about it is, if they vary at the same time, slightly in the same direction or strongly in the same direction, one gets large, the other one gets large, then one will be predictive for the other. If you know one, you will know something about the other. That's pretty evident. So the sample covariance is actually very similar to the sample variance. If you look at it, if you go back and you look at the sample variance and the sample covariance, it's the same expression. It's a deviation times another deviation. For the sample variance, that deviation is multiplied by itself. That's why we square. We usually don't think about it in that way, but if we go to the covariance, then we indeed see that we multiply some deviation by another deviation, and we sum that over all subjects. In other words, this is going to be positive if typically the 2 terms are both, the 2 factors are both positive or both negative. If you multiply 2 positive numbers or 2 negative numbers, you get a positive one. If they typically differ in sign, then what you would have is that you multiply plus with minus or minus with plus typically, and then you get a negative covariance. So it gives you the sign gives you the direction in which they vary together or vary against each other. Okay. Now, that said, SJK is the typical notation we use for a covariance, Sjj is just a special case where j and k are equal. So a variance is nothing but a covariance between a variable and itself. We tend to write S square and sigma square in the univariate case. So that leads to the somewhat confusing double notation that Sjj is equal to Sj squared. That's not a theorem. It's not a result, not something you prove. It's something you and I agree upon to denote it this way. It's just a matter, or you and I, Johnson and Witcher also do that, what is very common in the literature. If you remove the denominator, 1 over n, if you take that away, you simply get a sum of squares in the univariate case, but this is not a sum of square, what is circled here, and if we only circle that, this is not a sum of squares, it's a sum of cross products. So we call that a cross product, a product of one thing with another thing, and that we sum. So sum of cross products. But the whole thing together is then called the sums of squares and cross product matrix. Univariately, it doesn't happen. Now you may tell me wrong, because in regression we also see that. Yes, if we talk about various parameters, of course. Univariate regression means univariate y, but you may have several predictors. So that leads to several betas in the regression course. They have information, they have variance covariance matrices, so we're already used to it there and then. So W will often be the matrix of sums of squares and cross products, whereas S is the variance covariance matrix. Good. Okay. The correlation coefficient is well defined, well understood, well known. It's nothing but the variance divided by the covariance, a covariance, divided by the square root of the corresponding variances. In this way, it's known, it can be shown, and that's technically the Cauchy-Schwarz inequality for people who know that, and for people who don't know that, I'm not going to explain it, and we don't need it right now, but that comes back in the multivariate course in year 2. Anyway, from that particular result, it follows, as you know, that the correlation lies between -1 and +1. If you do a calculation and your correlation comes out 4.7, it's not a bad idea to do the correlation again, because likely something's wrong. So a correlation lies between -1 and +1. That's a necessary condition, otherwise it's invalid. It's not a sufficient condition. We will come to that, and that's important. Correlations have more restrictions than lying between -1 and +1 unless there is only one. By that I mean, if I give you one variable and another variable and that's it, so bivariate, that correlation between those two guys can go from -1 to +1 and everything in between. If you have 3 variables, there are of course 3 correlations between the first and the second, the first and the third, the second and the third. Well, what would that lead to? It would lead to a variance covariance matrix and correspondingly a correlation matrix. So, for example, if we take such a correlation matrix, we know for sure it looks like this to begin with. A correlation matrix has 1 on the diagonals. And then, if you take the sample values, you have R12, R13, R23. Now I can say these R's must lie between -1 and +1, and I'm not lying, it's true, but that's not enough. So, for example, if I choose that matrix to be 0.5, 0.5, 0.5, it's valid. If I make it -0.3, -0.3, -0.3, it's valid. If I now make it -0.9, -0.9, -0.9, it's not valid. This is not a correlation matrix. You might say, hey, but all the correlations are between -1 and +1. This must be valid. No, it isn't. There is a stronger condition. What is it? What condition must apply for a matrix to be a valid correlation matrix, or for that matter, a valid variance covariance matrix? What condition is that? 16th letter of the alphabet. starts with not negative, but
Maybe because minus 0.9, so maybe the second and the third are the
yeah.
Opposite direction.
Yes, exactly.
The first and the second opposite direction.
Yeah.
So maybe the
Yeah.
first and the third should be on the same direction.
Right, exactly.
Yeah.
So I mean, there is a mathematical result and there is intuition, and you're giving me exactly the right intuition. So what you're saying is, if they all would be minus 0.9, take it a little bit further, make it minus 0.99999, so you were approaching minus 1. It basically means that essentially the first variable and the second variable are opposite. The second and the third are opposite, but if that's true, we're back to where we were. If the first is opposite to the second, is opposite to the third, I'm back where I was, and the first and the third are the same. But no, it says the first and the third are also each other's opposite, and that's not possible because opposites is plus and minus. There is not a third direction in which you can have an opposite. So it's the interplay. Three variables at the same time a dance that's not allowing every possible step that you have in mind between the two of them. Otherwise, there is no harmony. So the condition is positive definiteness. Positive definiteness is important. Every variance-covariance matrix, S, or derived correlation matrix must satisfy the requirement of positive definiteness, and that's definitely something that will come up as we go. Okay. The correlation is unitless. You can actually show that. The variance is not. For example, in the iris data set, the variances and the covariances are in millimeters squared. Why? Because the measurements are in millimeters. You have the length and the width of both leaves in millimeters or in centimeters. It doesn't matter, but whatever you choose, the variance and the covariance is going to be the square of those units. That's why, intuitively, standard deviations and standard errors are a bit easier to interpret because they're back to the original scale, centimeters and millimeters. You can say, okay, the average is 17 plus or minus 3 millimeters. It would be a little awkward to say 9 millimeters squared. We can deal with it as statisticians, but that's much more difficult to picture. Correlations, though, you have millimeters squared in the numerator. You divide by millimeter squared times millimeter squared, square root thereof. So millimeter squared divided by the square root of millimeters to the fourth, that's 1. So the units go away, correlations are unitless, and that's very difficult to expect otherwise. Otherwise, it could not lie between minus 1 and plus 1. You cannot have something restricted to an interval and have arbitrary units, because you change the units and the interval would change. It's not possible. It must be unitless. 0 means no linear association. It doesn't mean no association. There are types of association that are not captured by the correlation. And again, I don't want to go too far in that now, but let me give you one very simple example. Suppose I have a variable x and y with only 5 possible realizations, minus 2, minus 1, 0, 1, 2, and y has values 4, 1, 0, 1, 4. Are these two variables correlated? No. That hurts your feelings, huh? You're saying, but how can that be? One is the square of the other. They're not even in a stochastic relationship anymore because y is equal to x squared, and the error would then be 0. Knowing x, you know y. However, that's exact. I mean, what was on the slide? Linear relation. So there is a quadratic deterministic relationship. But if you try to build a regression model, you can try it linearly. Y is beta 0 plus beta 1 times x, let me put an I for observation, plus epsilon I. The coefficient beta 1 will be 0, and the coefficient beta 0 will be 0 for centering. Why? Because there is no linear association. It's pure. I mean, you see that here also. There is no linear association. Everything is in the quadratic term. So what you are saying, but you didn't say it, but that's what you meant, is the two variables are deterministically dependent. They are fully dependent. They are perfectly associated, but not with a linear association measure. There is no cubic association. There is a imperfect quartic association, etc. So what is this saying? This is saying either there is something wrong with the correlation or there is something wrong with my understanding of dependence. No, dependence and correlation are different. The correlation is just one measure of dependence, and you now understand the limitations of it. It doesn't capture all associations. It's a summary measure like every other summary measure. I can give you the mean and a variance of a variable, and yet I can have another variable with the same mean and the same variance, but they may have a different kurtosis, a different skewness. So they can differ in more. You don't know everything if you know the correlation. That's the key point, and there may be other, perhaps even more meaningful associations to consider. Okay. Linearly, though, they have very nice features. Like if you take a linear transformation, the correlation doesn't change, perhaps except for the sign. So that means if you transform, what kind of transformation would this be? Well, for example, you might transform Celsius to Fahrenheit. If you do that, the correlation remains the same. The only thing is if you change the sign, so if A or C would be negative, then the original versus the new correlation may flip signs, but that's not so important as long as it's important for the interpretation. But think about it. Think about the NTP data. We talk about weight. Weight goes down as dose goes up. Malformation rates go up as those go up, so they're negatively correlated. But the two effects, we could say, are correlated, because weight loss, if you would qualify weight as decrease in weight, you would have a negative weight, right, or a negative weight difference. That would correlate then positively with the dose effect. So it's all a matter of coding. One problem is correlation is sensitive to outliers. Variances also. The moment you, and we will not spend too much time on that in this course, but it's just good to know that quadratic measures and correlation measures, of course, they blow up an outlier even more. If something is large, the square of it will be even larger. That's the intuition behind it. So always explore a little bit what you find. Always explore a little bit how sensitive your conclusions are to outliers. And definitely look at the data graphically. Okay, distance. Distance is a key concept in multivariate analysis, and we of course know very well Euclidean distance. We can take a piece of paper, like I'm doing now. We draw an axis system with, let's say, longitude and latitude. We have 2 points, and we can calculate, for example, the L1 distance, or we can calculate the Euclidean distance, or many other distances. Is that okay statistically? Yes and no, because distance in statistics depends on a few other things. So Euclidean distance is a good basis to start from, and what I just drew is actually the same as what I indicate here. So of course, I'm working in p-dimensional space. We are statisticians. We don't work just with bivariate data. We work with multivariate data. Think about the iris data set. P will be equal to 4, so we can calculate, in a way, the distance between 2 flowers. The distance, of course, making use of the 4 variables that we measure on those flowers. We can write it in several ways, of course, because to quickly illustrate what I wrote in the formula, the easiest thing is to say the distance is yij minus y1j minus y2j squared. That's a square distance, where j goes from 1 to 4 in the iris data set, p in general. That's a square distance. There's a square root in the slides, as you see in your notes. But if I don't write that right now, it's okay. I can just as well say this is y11 minus y21 comma or semicolon, 1, 2 minus 2, 2, semicolon, etc., multiplied then with the column vector y1 minus y2, y1, 2 minus y2, 2, etc. So we multiply the first element of the row with the first element of the column, the second of the row with the second of the column, etc. But it's exactly what we did the line before. Yes?
No, I didn't get this part. Are we measuring the distance between the flowers or between the petal and the sepal?
We're taking two flowers, and we're taking their 4 measurements and we're calculating the distance between the flowers as such, in terms of the 4 variables. Yeah. The distance between petal and sepal, that's actually also a distance question, but that's more canonical correlation and we won't get there in this course. I mentioned it, but we won't do that. But what I'm doing now is kind of more the abstract definition of a distance. You can say, forget for a moment about statistics and say, these are 2 houses in a city and I know their X location and their Y location and how far are they apart from each other. Depending on the city structure, or the area structure, it may be easier to just draw a line between those 2 houses and measure, or say, no, we're actually in New York City, so the only way to go is this way and that way, for example, and then you take another distance. There are several options. So what I'm getting at now is we can denote that in a variety of ways. And shorthand notation is this. The bottom here, it's the vector y1 minus the vector y2, of which I calculate the distance between them, of which I calculate the 2 norm. The distance that we calculate here, the classical good old-fashioned Euclidean distance, which is what happens if you throw a yardstick on the floor and measure the distance, that's the Euclidean distance in its basic geometric form, as many of us know quite well. Now, as I go, there may be 2 situations. You're very familiar with this, or you're not, or something in between. I will go over it, I will use it, but even if you say it's a little, I knew it, but it's a little rusty, you have to revise it later, but it won't stop us now from continuing. But just take the time to then revise it later a little bit. And there are many good sources, but a good source in particular is the book by Johnson and Wichern, who has extensive background on that. You may also measure the distance between a point and the origin. Now the origin, what is that? 0, 0, 0, 0. And therefore, something minus 0 squared is just the something squared. So that's just the sum of the squared observations. Very rarely will we use that in statistics because it's always the distance that we need, almost always the distance between 2 things. For example, a mean and another mean. And why would we have 2 means? Well, think of the iris data set, the average setosa and the average versicolor flower, how far are they apart? We may want to answer that question. How far is a particular setosa flower away from its mean as a group? How far they are away from 0, it's not so very relevant because there is no flower in 0. The 0 flower by definition doesn't exist. So we're more interested in really genuinely biological comparisons, and that usually means we compare relative to something. You know that from ANOVA, univariate ANOVA. Do you talk about deviations or sums of squares, etc.? You do, but usually they are corrected sums of squares, mean corrected. The actual overall mean, the grand mean as it's sometimes called, is irrelevant. You take it away, you take it out of the equation. And that's why you have, for example, 300 degrees of freedom, you do a degree of freedom decomposition, and it adds up to 299 because that overall mean has been taken out. I will come to that graphically in a moment. Now, if we turn to statistics, there is actually a little bit of an issue because distance may all of a sudden not be the distance that we use, for example, when we measure distance between houses or on a piece of land, etc. And I'll give you an example how distances can actually be slightly more general. For example, if I ask the question, is the distance between Hasselt and Brussels equal to the distance between Brussels and Hasselt? Depending on how you look at it, the answer is no or yes. If you just measure geographical distance, like geometers would do or like geographers would do, they would say, of course, it's the same distance. However, if you're in, let's say, traffic policy, you may say in the morning rush hour, the distance from Brussels to Hasselt is in time much, much shorter than the other way around because you're stuck in a traffic jam. So these travel distances, or travel times actually what I'm referring to, may come into the equation. Statistically also, if I have, for example, and I'm going to keep it very simple, a situation where I have a length variable and a width variable, I may, and that's what you really have to keep in mind, I have to first see what is now the structure of that space. In Euclidean space, I draw a space, and even though I did not norm the space as mathematicians call it, what is norming a space? It's putting a 1 on the horizontal axis and a 1 on the vertical axis, and you expect me to take a ruler, 1 centimeter horizontally, 1 centimeter vertically, and we have a nice square piece of paper with square little boxes on it. However, if I now draw a cloud of points, and I don't like to do it all the time with these crosses, it's boring, it's tiring, so usually I symbolize it by an ellipsoid. There is a little bit of a hint that I have a normal distribution because the multivariate normal distribution produces contours like that. The univariate distribution, the univariate normal, looks like a bell. In 2 dimensions also, but there is of course also the correlation structure, and that means that, for example, the length and the width, the way I drew it, are correlated. They're positively correlated, and that's usually seen by something that lies in the 45-degree line direction or more or less. If you want negative correlation, of course, it's going to go the other way. Then you might have, and this would be a very strong negative correlation, you may have a picture like that, meaning that if one variable gets large, the other one gets small, and the other way around. Not now. Here, and I think that's biologically plausible, you say if the length increases, typically also the width increases. Now, Willy brought several colors, so we can use a few colors right now. I can now say, let me indicate the mean. That's the overall mean of my population, either because I calculate the average of my 50 flowers or because I know, theoretically, I'm doing a simulation experiment, I know the mean, whatever. Now, the question is, which point lies now furthest from the mean? The green one, or let's hope this is blue, the blue one. Well, Euclideanly, in a Euclidean fashion, it's clearly the green point. But if you look at the ellipsoid, you cannot help but notice that the green point lies outside my ellipsoid and the blue point lies inside. So in a way, statistically, this blue distance is shorter than the green distance, even though if you measure it with a ruler, it would be different. So why is that? There is the intrinsic variability. The length may be more variable than the width. One variable may be more, one thing that you measure, so one variable, may show more variability, more spread than another one. And so it means if there is a lot of spread, if there is a lot of spread, a large deviation is not abnormal. That's what you would expect, because that means large spread. But if there is a very small spread, a very narrow spread, so very tight relationship, and we see that in the IRIS data set for some variables. Some of the width variables really have a very narrow range. If you then have a large value or one that is small and deviates from it, it's a clear different value. So, in other words, everything is measured relative to the precision on that particular variable. That's the first thing that we need to keep in mind, and you see that we have attempted to do that on the slide. So the distance of a point to the origin actually takes the scale into account. And what I've done here, I could indicate then on a piece of paper by saying, well, for example, in one direction, and now I'm exaggerating, I have a huge unit. In the other direction, I have a small unit, something like that. So before actually measuring the distance, that's another way to think about it, I first, tell me if I'm not doing it properly, huh? I first calibrate. And that's what I do. I divide by the precision. The advantage also is that the moment you do that, your distance becomes unitless. Look at it. Y is in millimeters. Y squared is in millimeters square. You divide by the S square, which is in millimeters square. So millimeter square divided by millimeter square, that distance becomes unitless. There is a very important advantage as well, and that's a motivation in its own right. If you would have had now the idea to change millimeters to centimeters, you're going to inflate your Y by a factor 10. If you go, no, the other way around. If I go from centimeters to millimeters, Y inflates by a factor 10 because 1 centimeter becomes 10 millimeters. 1.2 centimeter becomes 12 millimeters. So Y inflates by a factor 10, Y squared by a factor 100, S squared by a factor 100, and that cancels. So like a correlation, this distance is properly calibrated because honestly the units are not important. You can go outside and measure the temperature in centigrades, or you can measure it in Fahrenheit, but it's going to be equally cold. You're not going to change the weather by measuring it in different units. It is what it is. So if you capture an intrinsic, here we would say geometric feature of the data, it should not depend on the units. And so we're on the right track. I have one problem though, because the way I do it now, here, I take the variability into account, but I feel I'm missing something. That's good news and bad news, because the good news is we can come up with something more elegant. The bad news is there's more work to be done. We don't take the covariance into account. Because think about it. Let me go again to a few very extreme situations. If I have a cloud of points like this, it's good to start to think geometrically also. It's always a little easier to understand what's happening. Or one like that. Or one like that. I have now 3 different situations. In the first case, the first variable and the second variable have about the same variance. And the cloud of points is not oriented in one direction or another. It's just a circle. So that means knowing one tells you nothing about the other. So this one is equal variance. S1 square is equal to S2 square. Rho would be equal to 0. But in this case, the variability in this direction is much bigger than the variability than in that direction. So S1 square is much bigger than S2 square, and the correlation is actually still equal to 0 because there is no orientation. It's just a horizontal orientation or vertical orientation for that matter. So there is no information in the first variable about the second one. In the third graph, yes, because if I know that my first observation is here, look, we might say plausible values of the second one might be in that region. But if I make an observation here, then actually plausible values change entirely their region. Now what I'm doing here is a very rude, crude way, rough way of prediction. I'm predicting the second variable out of the first, and of course not perfectly. I might even miss the interval a little bit, but on average, I might say if the first observation is small, so will the second one be. And that's of course in biology the case. Look at your own arms. If I know the length of your left arm, I can predict the length of your right arm. Not exactly, but pretty much so, because the correlation is 0.99 for most people. Otherwise, we would be looking quite funnily. That's exactly what we're saying here. You know a lot about one thing if you know the other things. Okay, but That's nowhere in our distance yet. So we need to translate that into our distance, and the question is, how do we do that? Well, before I go there, sorry, one more specific case. I can now make that last graph a little more extreme and go to an ellipsoid like this. And you see what's happening in the end. It's disappearing in a line. In this case, the correlation is equal to 1. Here it may be the proverbial 0.99, very high. In that left-hand cigar-like form, I might say, well, if I know y1, I'm not sure about y2, but almost. I'm nearly sure about what y2 is going to be. In the second case, there is only one variable. You measure 2, but it's actually only one piece of information. Okay, so what would this be? For example, if X is the temperature in centigrades, and you happen also to measure the temperature in Fahrenheit, you may have a graph like this. Or if there is a little bit of measurement error, you may have the graph on the left-hand side, but that's what you would expect. In that case, it's almost fair to say, yes, your bivariate problem truly is a univariate problem, because if you know one, you're not going to learn a lot about the other one. If you know the temperature in centigrades, the only one the Fahrenheit temperature is going to tell you is your measurement instrument precise? And if it's precise, you're really not learning anything new in terms of biology. So the question is, in the iris data set, are the flowers now, for example, do they have leaves that are bigger or smaller, but other than that have always the same shape? If that's the case, the only thing you need to know is the length, or the width, or the surface, or the circumference, because one quantity will capture both. You may measure 2, but you actually only get one piece of information. Reality is usually somewhere in between. If you measure something else on our own biology or on the iris's biology, you get more information, but not independently, and not nothing, somewhere in between. And that's, of course, the playground of where we are. But we want our distances to capture that. Now, what we do here on this slide is we're playing an old mathematical game. What do good old-fashioned mathematicians do? If they have a difficult problem, they solve another one. Is that a clever idea? Yes, if the solution of the other problem is equal to the solution of the original problem. So I have a problem, I move to another problem, I solve that one, and then I return the solution to where I was. So I make a little detour. If that street is too busy or too dangerous, let me go round the block. That's essentially what we do. And that's exactly what we will do here. And for that, we use the concept of transformation. So, we're not going to see too many proofs in this course, but this is one. Because this concept of distance is indeed quite important. It will help us to define a statistical distance. That's the outgrowth, and that statistical distance will be used for the rest of the day. So we need to understand that a little bit. We have our variables, y1, y2, y3, y4. So we do have those for each and every one of the 150 or the 50 flowers. Yes, and this way you see it better, indeed. Thank you. So these are the 4 iris measurements. But now the idea is that they have variances, they have covariances, and life would be a little easier if that would not be the case. Now, they're always going to have variances and covariances, but what if we can set these covariances all equal to 0 and the variances equal to 1? What would the variance-covariance matrix then be? The identity. Of course, I cannot force the flowers to be that way, because then I would be fiddling my data or ruining the flowers. That's not the idea. So what I do is I transform those variables into new variables, and I define, and that's my own invention right now, our invention, I define 4 new variables that are linear combinations of the old variables. So there is C11y1 plus C12y2 plus C13, etc. We can spell it out. Okay, and then the requirement is that that C the C that we are using here leads to a unit variance covariance matrix. So in matrix notation, and that's also what you see in the slide, xi is C times yi. And now what is this C? How should I choose this C? Well, that's precisely the point. I don't know yet, so I want to derive that. The only thing I have is y. I have y, I have the y space, I have the y observations, so I have everything that derives from the y. So what I have is, let me write it down on the side, y and the corresponding s. That's what I have. What I want is the variance of x to be the identity. So for that I'm actually going to say the other way around, y is C inverse times xi. And what is then the variance covariance matrix of the C's? Well, it's going to be I. That's what I want, but that's then 1 over n, sum of xi minus x bar, xi minus x bar transpose. This is the sums of squares and cross products. And just to fix ideas that this is indeed the matrix that we are thinking about, we spelled out before each one of the variances and the covariances separately. Many people find that easier because you see either the whole matrix spelled out or you get element by element, but this is much more convenient to write down. Does it have the right form? Yeah, because this is a column. By default, it's a column. This is a row. And if I multiply a column by a row, this way, I get a matrix. If I multiply a row by a column, it becomes a number. But this way, it becomes a matrix, and that's exactly leading to the variance covariance matrix. Now, I'm actually using, and I will be using a few properties that either you know or you don't, and if you don't know them, look them up, but I will just say what they are, and we use them. So what is the x? The x is C times y. That's my definition. So the x is C times yi minus, the same applies to the mean, no problem, C times y. And then I have the whole thing transposed. Forget about that transpose for a moment and say this is again C times x minus C times x bar. Okay, so let me write it like that then. C times yi minus C times y bar. Transpose, so 1 over n, sum over I, and now the C I can put to the front, yi minus y bar. I can do the same here, move the C to the front, within the square brackets I can move it to the front, but transposing a product is transposing each one of the two factors in different order. AB transpose is B transpose times A transpose. They get in different order. So that means I get first the y's, either you know the result or otherwise you don't and you say, hey, that's strange. And yes, once you've seen it, it's okay, but that's a well-known result in matrix algebra. But now, the good news is that I actually have a sum over i's, but the C is independent of the sum. So let me move the C's to the very outside. yi minus y bar, yi minus y bar transpose times the C transpose. And what is that middle bit? That middle bit we know. The middle bit between the curly braces now is only in terms of the data that we have. So that is the S matrix with which we started, because there is now no transformation here anymore. This is just S. So let me repeat that last thing. Where I am now is the identity matrix is C times S times C transpose. What is unknown? Unknown is C, yes. S is given, E is the identity matrix, and that's pretty much known. Huh? If any matrix is known, it's the identity matrix. So this is my requirement right now. But what I can do now is say, okay, this equation here needs to be solved somehow. So what I'm going to do, I'm going to choose, for example, and that's also the final solution in the notes, choose S equal to C transpose times C inverse. And I'm doing it this way because I know it's the solution, but let's see that it works. So I fill that in. E is, the identity is C times C transpose C inverse C transpose. Is that okay? Just like transposing, does inverting change the order? And that's good news, of course, because I get C inverse, C transpose inverse, C transpose. But as far as I know, something times its inverse cancels. And indeed, it's the identity matrix. It's satisfied. So do I know C right now? Yeah, I do. C transpose times C minus 1 is equal to S. So that means C transpose times C is S inverse. I know C. Well, I know a function of C. Univariately, we would say we know the square of C. Here it's C transpose times C because it's the matrix. We're close to the solution, and that's indeed the solution that we have right now. But C itself, we don't have yet. But the thing is, the trick is now, don't get carried away with calculating the C. Just know what we would like to do. What we would like to do is calculate the distance between 2 points, and the distance is coordinate independent. So do that in terms of the original axis. What is the distance if in the do that in terms of the new axis, the transformed axis, just like in the original y units. So the axis, what is the variance covariance matrix of the axis? The identity. That's what we just constructed. So that means at the x level, I actually have for the distance the Euclidean distance. What I circled is the Euclidean distance question. Well, the thing is, I'm almost there. But the thing is that if I transform my data to new data, but I'm actually not changing the data, as we will see, I'm looking at them in a different way. But by doing that, I bring it back to a problem that I can manage. I know if I want to calculate the distance between points, and those points live in a space with unit variances and zero covariances, then I have the so-called Euclidean space. So in the X space, I can solve a Euclidean problem. But of course, you may say, why do you want to do that indeed? And that was your question. Because we live in the Y space. The X space is something you made up. We want to go back to sepal length and sepal width, etc. Okay, fine, I'm going to do that now. So once I have that solution, I'll go back to where I was. Think of the mathematician who's making the detour. And then I will have a solution in the original units, and we can forget about the X's. So it's just a device. It serves our process, but once the dish has been prepared, we don't need a cooking pot anymore. So the X is the cooking pot for the time being. All right. So if we do that now, with that, it's a very good question because indeed it reminds us that we are doing the right thing. So if I write that down here, the distance between P and Q is indeed x1 minus x2 transpose x1 minus x2. Why? That's what we just said. The x's live in the Euclidean space, so there's no correction necessary. But I want to go back to the original x's. So the x is actually c times y, y1 in this case, c times y2 transpose, c times y1 minus y2. Okay, the transpose, we get used to that in the meantime, means we change the order of the factors. So y1 minus y2 goes to the outside, c transpose to the middle, c, and then y1 minus y2. All right. Now, question.
Why is the distance squared?
Sorry. Oh, no, you're totally right. That square should not be there. Very good question. So this 2 is a mistake. It's just the distance between P and Q. And if we write a 2, it should be D2 or something like that because it's the Euclidean distance. That square is a mistake. Yeah, thanks for pointing that out. So now we're actually quite lucky because we did not bother deriving the C from the S. And good thing that we didn't, because we don't need the C, we only need C transpose times C. So we get y1 minus y2 times S inverse y1 minus y2. And you don't see that, but now you do, right? I'll keep making that mistake, not on purpose, but you'll have to be vigilant. Huh? There are many referees to correct me if I'm wrong, so I'm glad for that. And I appreciate that. Huh? That's what statistics is about, precision, and we help each other in reaching that precision. And as one gets older, one makes more mistakes, not less so. Okay, so now I have something not written so nicely. It's a little nicer actually here, where I still made the same mistake. Huh?
Yeah, I think it's correct because
Yes, yes, yes.
at the square root.
Yes,
So it should be
it's the square distance. Yes, it's the square distance. Yes, I was wrong in saying that it was wrong. Yes, good. We'll get there together. Indeed, it's a square distance. Yes. Sometimes we write a norm symbol with a square, etc. Yes, good point. So this is the square distance indeed. But the good news now is, at this point, where is the x? The x is gone. Where is the c? The c is gone. The c was a device to get where we are. The cooking pot has disappeared. We just have the dish on our plate and we can eat it. The statistical version of that is we can now start using that distance, which is entirely in terms of quantities that we know. The actual data, y1 and y2, that's what we measure, and the variance-covariance matrix of those. So somehow we are not surprised that we see these variance-covariance matrix showing up, because we had gotten as far as saying if the range of the variables is different, we have to correct for that, but now we correct for the whole thing multivariately. Question?
I'm not really clear with, I think that for the transformation at some point we started with considering that we're transforming or wanted SX to be the identity matrix.
Yeah.
I think that was an assumption. I don't see how we are back to norm for getting that.
Yeah.
Because if we're using this transformation, then we are carrying that, are we carrying that assumption?
Yeah. Yeah. So the question is, we made the assumption about the x, that there was an assumption that the x should have variance-covariance matrix 1. What's left of that assumption? Well, the answer is simple, nothing. The thing is, the original data did not change. What we say is, let us derive temporarily, let us construct a new version of the data, a transformation of the data, in such a way that the transformed data have unit variance. So that's a question I can ask the question in a different way. Can we transform the data y into derived variables, linear combinations of those x that have unit variance? And the answer is yes, we found that such a C exists and satisfies this requirement. Every C satisfying that requirement does it. But then we say, okay, for such an x, we can use the classical Euclidean distance. But now, because distance should not change if we change coordinates, because distance actually is a geometric quantity. That means there is a point here and there is a point there. And whether my axis system is like this, or like that, or like that, my 2 points keep lying in the same place. So for the time being, for one moment, I changed the axes, and then I changed them back to where they originally were, and in that process, I have derived the proper distance that was derived from the x's, but now back to the y. So there is nothing remaining. That's not an assumption that actually is playing a role right now. It served its purpose, but it's completely gone. Yeah. There's no x's there. This, we can actually also derive it in, I see that you're a little skeptical, but what we are doing is we're using a device. We basically transform linearly and we transform back. For example, if I say x is 3 times y1 plus 5 times y2, and x1. And x2 is 7 times y1 plus 9 times y2. We transform, and we have new variables. But now we did that cleverly so that those new x's have unit variance. What I do at the end of the day is I just do the inverse transformation and recover my y's from my x's. So there is actually a consideration, and that is that transformation needs to be of full rank mathematically. I should be able to recover it. A simple example of a transformation is x1 is y1 plus y2, x2 is y1 minus y2, the sum or the difference. Well, if I tell you the sum of two variables is 7, the difference of two variables is 9, what are the original variables? You can go back. But then if you know the distance in the x space, you know the distance in the y space, because that happens to be the same thing. Yeah.
And is it the case that we can always get this transformation?
Yes, we just saw that. If the S is positive definite, so if the S is a proper variance covariance matrix, you can always do that. There's no problem with it. It always exists. Yes.
Is this distance affected by the unit measurement that
No.
reliable?
No. So the property about independence of units also applies here, just as it did before. If you change the units of y, you go from millimeters to centimeters in the y's, the s will follow along, and that transformation will entirely cancel. So many transformations you can apply to the y, because basically what I'm saying is you multiply all the y's by 10. If you do that, the s's will be multiplied by 10 squared. 10 squared inverse times 10, it's pretty much 1 again, so it always cancels. It's actually independent of linear transformation. Yes. You had a question also? No. You had a question?
Yes, actually, when you have this distance, you have not no c, right? C that is something
No.
that we just use. So it means that sy you also don't know. So
Well, the question is, do you know C? Because you don't know. What's the relationship between knowing the C and knowing the S? Let me put it this way. S you know. The S you know because you have a sample, let's say 50 setosa flowers. You calculate the variance covariance matrix, and that's your S. The
this s, sy,
Yes.
y equals 1.
Yes, that indeed you get from the data directly. That's the variance covariance matrix from the data that you have, because the y's are measured. You have your 50 times 4 matrix, calculate the variance covariance matrix, that's the S. So that follows from the data directly, and that's precisely the point. It needs to be, you need to be able to calculate it.
So I don't quite understand what is the advantage when you use this distance, because when you compare with the formula in 3.1 is because sy you also know, and for this distance you can calculate from your data. So why do you use on the transformation?
You say 3.1, that's here. Yeah, you can calculate this distance. It's a good point. Why not this one? Actually, the Euclidean distance is even simpler. Just don't use the S. Only it has a lot of very nasty properties. You change you change the units, and the Euclidean distance will change, and that's not the idea. This distance is invariant to transformations of the type that we discussed. But if you do linear transformations like x1 is y1 plus y2, x2 is y1 minus y2, this distance will change, and that's not what you want. So the one that is fully independent of linear transformations, the way we do all the time in statistics, is only the Mahalanobis or statistical distance. Yes, good question. Because otherwise you're basically telling me, well, we have many simpler things in the meantime. Why using that difficult thing? It's a good point. You have to be comfortable with this Mahalanobis distance, because it will not go away quickly in multivariate analysis. That's the key tool. Knowing Mahalanobis distances, being able to picture them, work with them, that's essentially, I'm slightly exaggerating, all you need in what's coming now. That's the essence, because everything is in terms of distance. And sometimes it's in terms of distance between species and within species, etc., and comparing these two. You've actually been using a simple version of the a univariate version of the Mahalanobis distance ever since you were in primary school, or perhaps ever since your first course in statistics, more realistically, because there is something that you used before. Maybe you may recall that. For example, if you have y bar minus mu squared divided by s squared, does that remind you of something? Sometimes you see a division by n, etc., but let's not worry about that. 20th letter of the alphabet. This is a t ratio. If you take it without a square, it's the t statistic, so the t-test is actually a Mahalanobis distance. You look at the distance between a point, a well-defined point, and another well-defined point. For example, this could be a sample average, and this could be an hypothesized value, the null hypothesis. And you see how far are they apart relative to the natural variability. Basically, what is the t-test? The Mahalanobis distance. And if that Mahalanobis distance is large, you reject the null hypothesis. If it's small, you do not reject the null hypothesis. It's as simple as that. And now we have a multivariate version of that. Okay, good. That's actually, yes, question?
So I just like to be clear about the X, you say the SX are variance covariance matrix for the variable only.
Yes, the Sx is the variance covariance matrix, but of the transformed variables. Huh? The Sy is the same thing for the original variables. Yes. I temporarily used the y and the x because I was manipulating two versions of the data at the same time. Now, transformation of data is something we will keep doing. Especially in principal components and in discriminant analysis, we will transform as the day progresses. So it's quite important to manipulate the two at the same time. Yes?
Just one question about the formula 341. So here the difference between P and Q, like in the above, I think the units are also, for example, if you calculate by math, the denominator and numerator both have a unit mass. So I think this difference also will not depend on the unit, because in the numerator is
Yeah.
s squared. Also in s treasure is
Yes.
s squared.
Yes. Yeah, but not in this. I mean, it does depend on transformations. It does not depend on units. So if you transform one variable at the same time, or you transform all variables at the same time, it's fine. But if you do like linear transformations where they become linear combinations, x1 is y1 plus y2, then this one will change. Because that affects the covariances, and this one does not depend on the covariances. The full Mahalanobis distance depends on the entire S, which is the SJJs, but also the SJKs. Yes. Yeah. So here this is a good start, but you are not there yet. We walked in the right direction, but we did not finish the trip. Yeah. Okay, good. All right. Matrix and vector formulation. I will be quite a bit quicker about this one because this is just a few conventions, and as I said, the Mahalanobis distance, and within and between variability, that's really crucial. Within and between variability, I just mentioned that it goes together with the Mahalanobis distance. What is a t-statistic? Nothing but a comparison of between variability and within variability. You take a random sample and you say, it's variable because the y bar is going to change if I throw my sample away and take a new one. So that is between variability between my sample and the null hypothesis. What is the S? The S is capturing the variability within my population. So it's between versus within variability. It's hard to find a test statistic that doesn't do that. Almost all test statistics compare signal to noise, compare between variability to within variability. is the message I get strong enough to rise above the noise level? That's basically what we're doing. That's what ANOVA is doing, and that's therefore soon what MANOVA is going to do. Only everything that you know in terms of sums of squares becomes sums of squares and cross products, and the Mahalanobis distance, guess what, will be on the forefront all the time. Okay, so for that a few more conventions. I write my data in vectorized format. I write my entire data matrix, if necessary, in a matrix format. So a data set is actually, a data set just consisting of the outcome variables is a matrix, with in the rows the independent replications and in the columns the dependent replications. Iris data set, I goes from 1 to 150, J goes from 1 to 4. Okay. So that's the multivariate setting. If you have a matrix, every scalar operation can be done quite easily. And what is a scalar operation? Taking the expectation. What's the expectation of a matrix? The expectation of every element of that matrix. And here, yes, there is a typo. So all the x's here should be y's, because otherwise this does not make sense. It's nothing to do anymore with the x from before. Sorry about that. So it's a typo. So we'll see a few x's there, and it's of course correct if you make that transposition. But here the idea is the expectation of the whole data matrix is the expectation of every element. So we know what the expectation is and its proper definition. In the discrete case, sum over the probability mass function. In the continuous case, in integration. You know that concepts of probability and statistics or other inferential courses, only what you have done once there or what you need to do once univariately, now you do p times for every one of the variables separately. The expectation operator has a number of very elegant properties, univariately also. What do you know about it? You know that the expectation of alpha y plus beta, and now I'm talking about a univariate variable, is alpha times the expectation of y plus beta. So the expectation operator is a linear operator, as linear as it gets. Also in vector format, the expectation of a sum is the sum of the expectation. And there it stops. It works nicely for expectations, nicely for linear function, but it doesn't work for nonlinear function. So the expectation of a logarithm is not a logarithm of the expectation, as you know. And if you say there must be exceptions, good exercise. Find a random variable for which this is the case. Good luck at 5 o'clock tonight. When the course is over, you may do quite a bit of mathematics to find that. And then the expectation of a linear form or a bilinear form is just the constant matrices to the side and the expectation just to the x's. All right. So notation for random vectors then. The population quantities in other words, we use mu j for every component separately, and we group the mu j's into a vector mu with the 4 means. It's pretty obvious. The same for the variance-covariance elements. We calculated sjk from the sample. The sjk's have expectations, namely sigma jk, and that's what they are. So the Greek letters are the population versions of the Roman letters that we used before. The S matrix becomes the sigma matrix at the population level. And of course, just like S, sigma is symmetric and should be positive definite. You can then calculate the population correlations, just like you can calculate the sample correlations. There's nothing new under the sun, it's that same thing. And you can actually, but we won't need it a lot, decompose the, we will need that again when we talk about GEE in class 7 or so. So that's still a while from now. But you can decompose the sigma into the correlations and the corresponding standard deviations. Let me do that for a second, because now that it's there, it's actually good to see what we mean by that. The whole sigma matrix can be written as sigma 1, 1 up until sigma pp. And then the correlation matrix, rho 1, 2, rho 1, p, and then here rho p minus 1, p, and then again that original matrix. Do we do that all the time? No, we won't need that immediately. It's just there for when we need it. We can decompose the variance-covariance matrix in the variances and the correlations. Often for interpretation, correlations are easier than covariances. If I tell you I have two variables, their covariance is 7.5. What does that mean? If I tell you their correlation is 0.9, that's a different story. Why? A covariance is a mix of correlations and variances, and because they're not separated, I don't know what that means. A variance, yes. If I tell you the first variable has variance 5 and the second variable has variance 9, you know that the second one is more variable than the first one. That's a little easier. But covariances, they are not so useful for interpretation. Good. Yes?
The last paper is different from the left node. The basis in left node is a square root.
Ah, yeah, but this is actually already that square root matrix spelled out. So what we have here, that diagonal matrix here, is written here. So if I write, yes, you're right. I actually should, this is the full variance. So either I should write sigma 1 through sigma p, and then it's correct because these are the standard deviations, or I should write sigma 1, 1 through sigma 1 p, and then the half should come in there, indeed. Yeah. Can I do that, the square root of a matrix? Yes, definitely if it's diagonal. It's no problem. You just take the square root of the diagonal if that diagonal is positive. Can you take the square root of another matrix? Yes, if it's positive definite. You can take the square root of a positive definite matrix, but not of any matrix. That's not possible. It's not unique. If it exists, it's not always existing. It may even not be unique. Okay, good. So that's the terminology that we use around those guys. Independence. We know what independence means, and there are very strict definitions of independence. Independence is not no correlation. Suppose we are in a June type situation. So I'm asking a question. Can you give an example of a variable, of two variables that have correlation 0 yet are not independent? Well, there is that example that I gave earlier, where y is the square of x. They're definitely dependent. They're not independent, but they are actually uncorrelated. So correlation is only one aspect of the dependence story. We're often misled by that. Often we confuse the two and we say they're equal. And there's a good reason for that. You can defend yourself and say, oh yes, I was confused by what? By the normal distribution. In the multivariate normal distribution, independence and correlation 0 is exactly the same thing. But the multivariate normal distribution is a very special one with very easy, simple properties that do not always apply. Now, a lot of the methodology that we will develop will be normal distribution based. So we will be in the easier setting, at least for the rest of the day. So there's no worry there, but it's not exactly the same. We have to be a little careful. Okay, so you can actually have explicit expressions for means and covariances, but this is the probability theory behind what we're doing. We don't need that in full. We don't need that in detail right now. We can look at independence, but of course we have to be a little careful with independence. There can be independence in the full formal definition. The independence between two variables means their joint distribution is the product of their individual distributions. But what if I have four variables, like in the iris data set? They can be independent pairwise, one by one, or two by two, or they can be jointly independent. And that's a different story. And in a CPS type problem or a statistical inference type problem is finding out actually examples where one independence applies but not the others, etc. Okay. But we know that in the multivariate normal case, we know, or I preview, it's not going to be so difficult. It's actually easier. So look at that arrow in the in this bullet point. The arrow goes in one direction. independence implies covariance equal to 0. The other way around only in the normal case. So in the normal case, the arrow goes two ways, but not in general. Sure.
You did say something about computer nature. You said correlation does not mean independent.
I said,
What is the difference between when you say correlation and then independent?
well, I mean, correlation is so correlation and independence. Independence was, we can actually look at the formal definitions for a moment. What is independence? Independence, for example, two variables are independent if a property applies for their entire joint distribution functions. Correlation is one particular parameter measuring one aspect of association. So that means independence is a broad concept. It applies to the entire probability distribution function, and that's everything there is to know about a random variable. But correlation is a very narrow concept. We can, for example, for binary data, we can calculate correlations, odds ratios, kappa coefficients. All these coefficients will have different properties and different stories. So it's only one way of looking at the problem. A very useful one because it's the parameter that captures association in the normal distribution, but it's indeed limited. Think of that example where one variable is the square of the other. They are uncorrelated, but they're definitely dependent because the joint distribution is degenerate because one actually follows directly from the other, yet they are uncorrelated. So, yeah. Okay, partitioning. Sometimes we need to partition, and here I would like to refer loosely to canonical correlation, which we will see later, where you might say I have a set of variables which I split into two subsets. And that's still a multivariate problem. It's actually multivariate plus multivariate. 4-variate plus 6-variate. So my vector splits into two subvectors. And what happens then? The mean vector splits in the same way. Means follow their random variables. They do exactly the same. The mean is almost like a mirror. What the random variable does, the mean does. So the algebra for the random variable and the algebra for the mean is the same. Not for the variance-covariance matrix, because that always does a little more. Why? Means are linear, variances are quadratic, covariances are, as we say, bilinear. They're linear in J and linear in K, so bilinear. So evidently, I have the variance-covariance matrix splitting into the variance-covariance of the first set of guys, the second set of girls, and then I have the covariance between the two. And that's why my matrix actually doesn't split into two components, it splits in three components. Sigma 1, 1, sigma 2, 2, but also sigma 1, 2. You may say, wrong, there is also sigma 2, 1. And I say, not wrong, because sigma 2, 1 and sigma 1, 2 are each other's transposes. So yeah, it's actually different, but the same thing at the end of the day after all. Okay, I think that's what we need to know. Now, this is what we sometimes call the elephant in the room, and not really, because we talked, the elephant in the room is the big phenomenon, the big aspect that we don't talk about, but we did. We mentioned the normal distribution. Why is the normal distribution so dominant? Well, as an applied statistician, we have to be careful not to fall in the following trap. You will learn as you go that many models are actually nice, beautiful, elegant, easy to deal with. You know the software, you have used it before, and therefore you want to keep using it. A good example is logistic regression. A good example is linear regression and ANOVA because it comes with such nice properties. You are being exposed, for example, to the generalized linear model, to the exponential family. It's elegant and it's beautiful. Only the data don't sometimes know that. The data may not have followed the same course as you did, so they just do what they want. And therefore, the data may fail to be normally distributed. Some people go as far as saying nothing in nature is normally distributed. Others go as far as saying almost everything in nature is normally distributed. And they both may have a point, in the sense that the normal distribution is a convenient fiction. It's a mathematical construct. But what makes its status rise above that of other distributions? Well, there are a few. First, data do tend to be approximately normal. When we say not normal, that's a very mathematical statement that's leading nowhere in data analysis, because we talk about what is a good model for our data. Well, approximate normality may be sufficient. And if it's not normal, we may give it a little bit of a push and push it towards normality. There's a name for that, transformation. We do a lot of transformations, hoping that after transformation the data are a little more normal or become normal. And then our good old friend Laplace, late 18th, early 19th century, showed what? Central limit theorems. So what does that say? Even if data are not normal, what we derive from them is normal. So mu hat, x bar, these guys are normally distributed. Think about maximum likelihood theory. Under regularity conditions, the maximum likelihood estimator is consistent and asymptotically normal. X bar of a sample, full stop, is consistent and asymptotically normal, right? You know that from concepts of probability and statistics, am I right? Under regularity conditions, right? What regularity conditions? Finite mean, finite variance. So what is a good counterexample? So what I'm saying is you basically toss a coin. Can anything be less normal than tossing a coin? I don't think so. It's 0 and 1. How can it be less normal? Yet, the binomial proportion, if I repeat that experiment long enough, the golden board, becomes normally distributed. In the limit, it's a normal distribution because the Bernoulli distribution is properly behaved. It's a well-behaved distribution. Which distribution has bad manners? It starts with the third letter of the alphabet. It's the token. Chi-square is well-behaved. Slightly less than the normal one. It's a bit more wild, but at the end of the day, it listens anyway. Why do I say it's more wild? The chi-square distribution has a big variance. So if you plot chi-square, if you generate, it's a good idea. Let me turn it around. Generate from a chi-square distribution this weekend or so, if you're bored with anything else. Generate from a chi-square distribution, and you will see that the classical chi-square will generate some really large values because it's positive and there are, but that's normal behavior. But there is one distribution that's untamable, that's very hard to keep control of, the Cauchy distribution. The Cauchy distribution doesn't have a finite mean, doesn't have a finite variance, yet it's a very simple distribution. It's CDF. So its cumulative distribution function, its probability function is extremely simple, yet it defies every study. Its variance is simply undefined. Its mean is simply undefined, so that one never leads to the, that doesn't satisfy the classical limit theorems that we know. See, but nobody actually jumped to say, oh, the Cauchy and this one and that one. No, because most models that we use in practice are well behaved. So that explains why the normal distribution is so present. The other thing is that the normal distribution so easily generalizes to the multivariate case. The univariate normal and the multivariate normal, well, as we go in this course, by the way, the Cauchy was here, as we go in this course, we will talk about the normal distribution, and you and I will be thinking all the time about the multivariate normal, as if it's the most natural extension of the univariate, and it is. It's not true for other distributions. Don't do it now, but think as we go about a few other distributions and try to think about what is their multivariate analog. For the normal it's easy, but for the others it's not necessarily so. Okay. Now, there is, of course, there are settings where the data are truly binary. The NTP data. The heat shock data, we have a continuous outcome, but the NTP data, if we look at the malformations, they're binary. So Yeah, their means will asymptotically be for large samples normally distributed, but that doesn't buy us a data model. So there we will need data models that actually do proper justice to the binary case. Iris data set, not so much of a problem. There we can use continuous data theory, give and take a few assumptions that might or might not be satisfied. So that finally concludes a long introduction. We still have a few things to do before we finish the multivariate part. Actually, it looks like we still have to start the multivariate part, but we've gone quite far. We have two main ingredients. We have a good distance concept, and we will tighten that concept as we go, and we have the multivariate normal distributions. These are two tools in our toolkits that will be absolutely necessary in what follows. And on that note, we conclude this session.